So hello everyone. So last two classes, what we did, we calculated the number of microstates manually by simple counting method. Like there were energy states, and we simply counted how many ways we can arrange them, and from that we calculated the microstates, and from the microstates we can get entropy and other variables from entropy like temperature, pressure, and so on. So uh, today, means what was there like like particles are there, states are there, and we have to arrange them to find the total number of for bosons. We saw that more particles stay in same energy state, same energy level.
அப்படி இல்லைங்க குரூப்ல
But
இருந்தா
for
ஏட்டாங்க
fermions, only one particle can stay in one energy system. But today we will see a system where there are some
நானும் பண்ணுமா
some g states.
அதுதான் நானும் சொன்னேன் சிக்ஸ் ஏன்னு சிக்ஸ் ஏன்னு இந்த பண்ணி கம்மி இருங்க இவங்க
And
சொல்றதே
this
ஒண்ணு
number of
கேட்க
states have energy, then we will try to find the number of ways we can arrange. I mean, there are many states. Let's put it as E1, E2, this is E3,
ஜிப்பு ஓபன் இருக்கா பேக் ஜிப்பு
so we have energy states as E1, E2, E3, and E4. Now let's consider each energy state is it has um, more, and let's assume these are as steps, and each step has sub steps like this E3 energy level. Let's assume like this step has many sub steps like these things. Let's assume there are some sub steps G with energy for this energy E3 level. So previously we what we did, we could put particles in the energy levels, let's say in these steps. Now we see that each step has some substructures. Like there are more than one occupancy, means there are more than one state where I can put my particles, but the energy still will be same, right? So this kind of system, what do you call this kind of system? We call this kind of system as degeneracy. Degeneracy means uh, there are more than one state with energy E, some EI, let's assume. So if there are more than one energy states EI, then I can put my particles in those states and still my energy, total energy will be same. Like, let's assume its energy is EI, and if I have, let's assume two particles, and I am putting like this. Their total energy will be 2 EI, or you can say this particle and this particle. Let's assume they are fermions, and we know we can't put two fermions in a single energy state previously, because our energy state were very discrete, and they were single states. So we were allowed to put one fermion on one shapes. But now, you see, if our energy state has some substructure, we can put our particle in their substructure, and we still do not violate the um, fermion rule that one particle can stay in one energy state. And this particle staying in this state will have energy I. This particle, if I put this particle in this state also, this will have energy, same energy, EI, and so on. If I put the particle in any of the substates, they will have same energy. So this kind of states we call it as degeneracy. So we'll see today if there are degeneracies in energy levels, then how to calculate the total number of ways of arrangement, right? Let's assume we have total number of particles as capital N, and uh, we have some energy levels. Let's say I, going from 1, 2, 3, and so on up to, let's call this state as ith state. Okay, so let's assume first for classical gas means we can assume them as classical marbles or balls. Then we can put any number of balls in any state. So uh, so let's assume I have some three balls, and I want to arrange them in three different energy states. So there are 3 to the power 3 number of ways I can arrange them if they are distinguishable. So similarly, let's see. Correct. You can compute this. Is it correct or not? So previously, what were we doing? We were arranging the particles in the energy states um, according to their identical or non-identical. If they are identical, we will use combination rule, some NCI. If they are distinguishable, then we will use this NPI, like combination and permutation. Yes. Permutation means I can arrange this. Let's assume this is A and this is B. I can arrange between them two as B here and A here. Then we will have extra number of ways of arrangement for the permutation case. This applies for distinguishable particle. And combination, if we consider identical marbles, then there is no meaning of arranging because they are very identical. If I arrange this here and this here, or then I put this here and take this here, they will look the same. So in identical case, we will use combination, right? So now the case is that each energy state has some substructures. Let's call it, there are G number of substructure in this ith number of energy state. So let's denote this as Gi. Similarly, each energy state will have their substructure. Let's call it Gi plus 1 and so on. So we will see uh, for different kind of gases what will be the number of ways I can distribute the number of particles in the energy states. So I'll not derive anything. I'll just simply state the formula and we'll go to problems. So let's assume first classical gas. So classical gas, they obey Maxwell Boltzmann distribution. So classical gas, they obey, as you might be knowing, this Maxwell-Boltzmann distribution. So we will see what is the formula for this kind of gas to calculate the number of microstates. So I'm denoting some different notation here with W because we will use sigma for some different parameters next. So let's write this as number of microstates in the ith state. Let's call it this ith state. This will be n factorial Gi to the power, sorry, Ci to the power Ni, where this Ni is the number of particles in the energy state I, and you can um, interpret this Gi as number of substates in energy state I, and finally we will divide this as Ni factorial. So as I might be remembering, we divide this n factorial because of identical particles. If they are non-identical, means they are distinguishable, only the numerator will be there. If they are identical, then we will divide with this ni factorial to decrease the number of extra counted states. So let me write this clearly. So for Maxwell Boltzmann distribution, the number of microstates in ith energy state will be n factorial Gi factorial Gi, sorry, Gi to the power Ni divided by Ni factorial, where this N is total number of particles and Ni is the number of particles in ith energy state. And Gi is the number of substates or degeneracy, whatever you can call it, or number of substates in ith state. Right. So, as sometime before I was telling you that there are three number of states and three particles, so we will have 3 to the power 3 number of ways of distributing. This is the same form here you can see. And this is kind of some fraction, means there are some arbitrary number of energy states and we are considering only the ith state and we are calculating the number of microstates for this ith state. So total number of and so similarly there will be some other state I plus 1. So total number of microstates will be summation over I wi, right? So this is the formula for classical gas. Next we'll see for fermionic gas. So fermionic gas, they obey Fermi-Dirac statistics or Fermi-Dirac distribution. So for them, the number of ways I can arrange particles in ith state will be g factorial divided by 9 factorial gi minus ni factorial. So it's like um, combination of um, gi. Why we have only gi here? Because we are considering this ith state as gi, gi number of substates. So, uh, equivalently, we can say there are gi number of states. And for fermions, we are allowed to arrange one particle in each state. We can't put two particles in the same state. So, this is the formula. This is the formula for distributing um, ni number of particle in the ith energy state, or if you like imagine like this ith state has some gi number of substates, so it's like as we have calculated previously, there are I number of states and we have some j number of fermions. The number of ways I can arrange them is this, right? Then come to bosons. So they obey Bose-Einstein statistics or Bose-Einstein distribution. So for this case, we can put any number of particles in any number of energy states, right? So for this case, if we calculate the number of microstates in the energy state I, will be Ni plus Ci minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. See, in the numerator, we have now Ni plus Gi. So we have extra energy levels. They see more seats, means bosons. Uh, this they sit more seats or steps than fermions. It's an analogy. You can say it like uh, there are three particles already for a boson coming out from outside. It's a empty. It's still empty for it. So it has some extra state compared to fermions. If for fermions case, if the situation is like this, if a fermion comes from outside to sit on these stairs, so for him only one possibility is there. But if a boson is coming from outside, it will see three possibilities. So for bosons, we'll have always one number of states. So number of microstates will be more for bosons also. So we saw three ways, three three ways of calculating the number of microstates for bosons, fermions, and classical gas. So now we'll apply this. So I have written it twice. Okay. So we have Maxwell and Fermi and Bose gas, and we have two particles. So we have n equal to two particles, uh, and two particles in ith state, and mm, whose degeneracy is 3. So degeneracy is 3. Find out the number of independent ways of selecting particles in a state. So we will find Wi here. So let's consider Maxwell-Boltzmann distribution first. That means classical gas. So for classical gas, we have distribution Wi equal to n factorial Ci to the power ni over ni factorial. So for classical gas, it's like Bose gas. So that means we can put any number of particles in each state. So uh, the number of microstates, it can be 2. This is the maximum number of particles I can put in the ith state. So for this case, what is the distribution? Number of distribution for Maxwell-Boltzmann in ith state. This will be total number of particles is 2 and degeneracy is 3, and I can put maximum 2 particles in a single state. Then I'll put this NiS2 and divided by 2 factorial. So this will be 3 square. So there are 6 number of ways I can put 2 particles in the ith state, ith energy state. Right. So similarly, for fermions, what is the distribution for fermions? This is Gi factorial divided by Ni factorial Gi minus Ni factorial. So for fermions, mm, the number of particles I can put in a single state is 1. Right. So for that, I can, and this will be 3 factorial divided by 1 factorial. 3 minus 1 is 2 factorial. So I'll have three ways of arranging this two fermion gas in, in this ith energy state. Yeah, let's quickly check this. There are three states. There are three degenerate states with same energy EI, and I have two particles. So what are the ways I can arrange? 0, 0, sorry, notation is wrong. So in these three states, I can put like arranging this particles as 1, 1, 0, 1, 0, 1, 0, 1, 1. So this is the only three possible way I can put these fermions in this degenerate states. As you see, they have same energy because they are degenerate, right? So next come to Bose gas. So we'll find the distribution for Bose gas in the ith energy state. So what's the formula? No, WPI is Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. So as they are bosons, I can put more than one particle in a single state. So what is the maximum number of particles I can put in each state? As we have two particles, so maximum number of particles that I can put in a single state will be 2. So Ni is 2 for me, and this will be 2 plus, and degeneracy is 3. There are 3 substates in ith energy state, and there is one there, and this factorial divided by 2 factorial and 3 minus 1, 2 factorial. So what it will I have, this is 4 factorial divided by 2 factorial, 2 factorial. So this will be, no, it's not space, I'm writing here. So this is 4 into 3 into 2 divided by 2 into 2. So this is 4. So I have 6 number of ways uh, I can arrange this Bose gas in this ith state with energy I, and its degeneracy is 6. So you see, for classical gas and Bose gas, the number of microstates are same. So it won't be same for always. It will depend on the question. Okay, so let's do one more problem like this, and then we'll go to next. Hmm? Let's assume now there are two states now with energy E1 and E2, and this state has degeneracy 2 and this state has degeneracy 3, and we have three particles. We have total number of three particles, and 3 is the degeneracy here. Let's denote this as G2 and this is Z1. So you have to calculate Maxwell-Boltzmann. For Maxwell-Boltzmann particles, we have to calculate the microstates for these two states, and for similarly we have to calculate for fermions, and for bosons also. As I was saying, the formula is for ith energy state. So we will calculate this first, then this again, then total number of microstates will be W1 plus W2. Right. So let's calculate W1 first. W1, yeah, for Maxwell Boltzmann. Uh, let me write the formula inside here. N factorial Gi to the power ni divided by ni factorial. This is for Maxwell Boltzmann. So we have n equal to 3. So 3 factorial. This is for Maxwell or classical gas, whatever you can say. So this is 3 factorial, and Gi we have 2 for the first case, so 2 here. And how many particles can I put in a single state? As this is classical gas, I can put 2 particles in a single state. So this will be to the power 2. This Ni is 2 for me for classical gas. In denominator we have 2 factorial. So this is 3 into 2 into 1 into 2 square divided by 2 into 1. So it's 12. So this is for W, let's say 1, and this is for Maxwell Boltzmann. So similarly, I have to calculate for the second energy state also. So W2 will be how many total particles are there? 3. So 3 factorial. But this time the degeneracy is 3. So 3 to the power number of particles I can. Oh, sorry. There are 3 number of particles, right? So as they are classical, I can put 3 particles in a single state. Or this you can say there are 2 degenerate um, energy levels with each with energy 1. So now I can put 3 particles in any of the single states. So Ni is 3 for me. Sorry. So this will be 3. So this is 3 now. So it's multiplied by 2 is 24. So first state is 24. Similarly for the second state, this is Ni is 3. So 3 factorial multiplied with 3 to the power 3, then divided by Ni factorial. Ni is 3 for me now. So this is 3 factorial. So you can cancel it. Now what is this number? 27. Right. So this is W2 for Maxwell Boltzmann. So what will be the total number of microstates? You can denote it as this symbol or W, whatever you want. So this will be the summation over Wi. I goes to 1 to whatever the given energy states. For our case, it is 2. So this will be 24 plus 27. This is 51. So number of microstates for Maxwell Boltzmann is 51. Okay. Let's check for
I have one doubt in it. So when we calculate for W1, Ni is 3, no? Since it is a classical gas, so the denominator it should be 3 factorial.
oh yeah, yeah, sorry. It's 3 factorial.
Yeah.
My mistake, sorry. So we can cancel 3 here, then we have to divide the whole answer by 3. So it's divided by 3. This is 8. So, this will be 51. This is 8 plus 27. And this is 35. So we have 35 number of microstates for classical gas. Now let's come to fermion. So what is the distribution? Let me write on this side. Wi is gi factorial divided by ni factorial gi minus ni factorial. So what is the question? We have two energy states E1 and E2 with degeneracies G1 equal to 2 and G2 equal to 3, and we have total number of particles 3. So now as we are having fermions, uh, what is the number of particles I can put in each state? This state has two degeneracies, there are two energy states. So what is the number of particles I can put in each state? So it's 1 for fermion. So Ni will be 1 for fermion. So I have all the numbers. Ni capital N, it's not needed. Now we need Gi now. So we have for first case G1, G1 is 2, N1 is 1, G1 is 2. So let's calculate W1 for fermion. This will be 2 factorial divided by 1 factorial 2 minus 1 factorial. This is 4 divided by 1 factorial 1 factorial, those marks. So I have 4 number of microstates for the first energy state. So let's calculate for the second. W2 for fermion. For the second case I have G equal to G2 is 3. So this will be 3 factorial divided by n is 1, so 1 factorial, then 3 minus 1 is 2 factorial. So I have 3 microstates for the energy state 2. So what will be the total number of microstates for fermion? This will be summation over this Wi. So this is 7. So I have 7 number of microstates for fermions.
Again, W1 state, in the numerator you have only 2 factorial.
Oh, that's
So it should be 2.
sorry, it's 2, right? What is it? It is supposed to be 2, right? For W1.
Yes.
Sorry, sorry. I didn't understand what is the mistake.
Numerator only 2 factorial, but you have written 2 factorial is equal to
Oh,
2.
yeah, I have mistake. Sorry.
That's the thing.
Yes, true. So it's 2. Sorry. So we have 2 plus 3, 5. So we have 5 microstates for fermions. Okay, now we'll check for bosons. So case is same. We have degeneracy 2 and 3, and we have n equal to 3. Let me write down the distribution here. For both gas, we have Ni plus Gi minus 1 factorial divided by Ni factorial Ci minus 1 factorial. So I have bosons now. So bosons, I can put any number of bosons in each state. So what will be the Ni? Number of maximum particles I can put in each state. I have total number of 3 particles, so Ni will be 3. So let's put this and calculate the um, first microstate for the first energy. This will be 3 plus degeneration is 2 here, 3 here. So it's 2 minus 1 factorial divided by n is 3, 3 factorial, g is 2, so 2 minus 1 is 1 factorial. This will be 4 factorial divided by 3 factorial. This is 4. The W1 is 4 for me now. So let's calculate W2. For W2, Ni is 3, still 3. Gi will change to 3, and there is minus 1. So this is factorial here, divided by Ni is 3, so 3 factorial. Then Gi minus 1, so 3 minus 1 is 2 factorial. So we have 5 factorial divided by 3 factorial into 2 factorial. So it's 5 into 4 into 3 factorial, and 3 factorial, 2 factorial. So this is 10. So I have 10 microstates in the energy state number 2. So what is the total number of microstates? It's 4 plus 10 is 14 now. So you see, previously we were getting same number of microstates for classical gas and bosons. 6. We were previously getting 6 for classical gas and Bose gas, but now we are getting different numbers for bosons and classical gas. For classical gas, we are getting more, 35 number of microstates. And for bosons, we are getting 14 now. So if you get any question like this kind, you can apply these formulas and calculate directly from these formulas. So, okay, let's calculate the bosons.
1 second, I need to see the question.
I didn't write this question. This is different question. We'll go to this question next. For this now, the question is, we have a total number of particles as 3, and we have two energy states ei, where I goes from 1 to 2, and uh, the first energy state has degeneracy, G1 is 2, and the second energy state has degeneracy, as 3. So calculate the number of the total number of microstates for classical gas, fermionic gas, and bosonic gas. Right. This is the question. So Ni will be different for this small ni. It will be different for different kind of distribution that you have to just calculate. If it is boson, then Ni will be the maximum number of particles. If it is fermion, it will be one always, and you can calculate using the formula. Right. Okay. Then we'll go to our next question. So for this next question, I have to tell you something about density of states. So we will define density of state. So density of states can be defined as the number of states per unit volume at energy E, or you can say this E comes under this envelope E and some fluctuation dE. So how many states are there between these energy states? It's E plus some small variation dE per volume. So this is density of states. Let's denote it as dE. So this will be mm, generally number of states per volume for energy E. And this density of states, it depends on the dimension of the space you are talking about. So this is the initial formula for it. Then uh, mm, one second. If you define the number of um, microstates, or you let's rename this. Let's call it a volume. If we are in 3 dimension, this is volume. If we are 2 dimension, then it's area. For 3 dimension, it's volume. For 2 dimension, it's area. And for 1 dimension, it's length. This is um, volume, means number of microstates with energy E, and its dimension is volume dimension. If it's not actually, it's, for three dimension, it's volume dimension. For two dimension, it's area dimension, and for one dimension, it's length dimension. Right. So we can define this density of state as um, the change in this then volume with energy. We can define this density of state as variation of this volume which depends on energy, and this that means this is the microstates or the volume space, or the whatever the allowed space with this energy E, and we can calculate the degree of sorry density of states for from this microstates as by differentiating this. So and density of state is the number of states in this energy level. That means it's indirectly I am saying this is the degeneracy of this energy state I. For continuous case, we cannot say this EI. This will, energy will be continuous. But for discrete case, I can name this each energy level as I. Then in that case, I can say there are some states with same energy, which I will call as density of states. And uh, as we are going general, I can go to three dimension also. Then I have to define this per volume, or for two dimension per area, or for one dimension per length. So I have defined this. Next, um, next we have to find the energy relation. So it will be very easier for us if we don't do this in energy space. We can take this to some other arbitrary space, let's say K, where K is my uh, wave vector. So I'm taking uh, my energy space to K space. So I'm taking from energy space to wave vector space. So I have to find some relation between E and K. So this kind of relation are called dispersion relation. The relation between E and K are called dispersion relation. So, so I can write this relation in general as E equal to some E0 plus some, let's take 1 second. So let's take a non-relativistic particle. For non-relativistic particle, we get some relation like E equal to P square over 2n, right? So this is a dispersion relation. So this P I can write as H cross K for my quantum case. So I can write this as, let's assume there is some initial energy E0, and this is H cross K square over 2m. So um, this is a dispersion relation for non-relativistic particle. Right. So we will then we can get a dispersion relation as some function like e to the power some arbitrary integer number or some um, half integers also. So depending on whether it is integer or it's half integer, we can name them as parabolic, parabolic dispersion or isotropic dispersion. Let's name this parameter as p, and it won't be in numerator, it will be in denominator. So it will be some function of 1 over p, something like that. No, for now it's in the numerator, we'll see. So I can write generally the dispersion relation as E equal to E0 plus C k k to the power p, where this is a coupling constant and k is my wave vector and p is my dispersion parameter. Right. So for isotropic case, for isotropic dispersion, I'll get some relation between k and E as k equal to some E minus E0 over Ck to the power 1 over P. This is derived from this equation. See, just substituting. So I got a relation like k equal to E minus E0 by Ck to the power 1 over P. This is general for isotropic or parabolic. Now, depending on this P value, uh, the dispersion relation will be defined. So, for P equal to 0, this relation will be called isotropic dispersion. But for P, oh, sorry, not 0, if it is 0, then we can't define it. So, for P equal to 1, this relation we will call it as isotropic. For P equal to 2, we will see if P equal to 2, what will happen. For P equal to 2, this Ks relation with energy will be some root over function. So this kind of relation we call it as parabolic dispersion. So by parabolic, you can do squaring on both the sides, and you will get some E, some proportional to k square. And this is a parabola. If you draw it in k versus E space, we'll get some parabola. So for p equal to 2 case, we'll name this as parabolic dispersion, and for p equal to 1 case, we will name this as isotopic dispersion. Now, Now I can check number of microstates or volume in this K space. I can define it as uh, this omega K equal to Ck, sorry, Cn K to the power n. So this is in K space. The volume is defined in K space here, and n is the dimension of space. C is the uh, just coupling constant or some constant, and it will depend on dimension. So for one dimension, it's length. So for length, C1 is some C1. C1 is 2. For two dimension, C2 is 5. For three dimension, C3 is 4 pi over 3. These are the coupling constant which will come with uh, k function. So let's see, for one dimension, omega 1 k, this will be 2k, and for two dimension, this volume will be pi k square, and for three dimension, this will be 4 pi k cube over 3. Right. Now we have to come to the energy space. From this k space, we have to come to now the energy space. So mm, one second. Okay, we have this relation, right? And in previous slide, I have taken this relation, the dispersion relation, which is derived from here. I took some general form between E and K, and I derived for K. Now I can put this K in my volume here. Now this will be Cn. K is E minus E0 by Ck. E minus E0 by Ck to the power 1 by P is there, and N is here. So it's N over P. So I can take on the constants outside, Cn over Ck to the power N of N by P, and this relation, energy relation, is E minus E0 to the power N by P. So I got my volume in energy space now. Now let's calculate the density of state. So as I said, this density of state, this can be written as a differentiation of this volume d of gamma over dE. Right. So what will be the general form for density of state? Density of state means number of states per volume for an energy E. So if we consider the classical case, means energy will be continuous, then we will take some range E plus dE, and we'll calculate the density of state. It's important. I'll show you why this calculation of density of states is important. It's like degeneracy that I talked few minutes back. Like it's uh, number of states in same energy states. It sounds like degeneracy. So it's degeneracy for our case. So we'll define some density of state, and we'll put we'll combine with some distribution. Then we can find um, number of particles or total number of energy for its distribution if the system is very high or very large, and or you can say in general we can calculate number of particles and total number of uh, energy of the state. So let's calculate this dn. So this dn will be there is n over p here. So derivative will be n over p constant cn over ck to the power n over p minus e0. This is n by p minus 1. So this is the density of states. Now uh, we want to calculate the total number of total number density for energy E. Then in that case, what will happen? I will denote this G as previously I denoted degeneracy as G. So this G of E I can write as summation over D, dn multiplied with some energy uh, means for this energy state. I'll take the summation from 1 to total number of whatever the total number of particles is. That means I am trying to calculate the total density of states, and dn is the density of state for a particular energy state ei. Then I'll calculate the total number density of state. Then this is the form. For continuous or classical limit, I can take this summation as integration. Then in that case, it will be dn of e t e. So it will go from 0 to some infinity. So why am I doing this? Hmm. Here, uh, a limit will be there, and this energy approaches to 0. That means I'm taking one range e2 e plus delta e or de, whatever you want to say. So I have calculated the density of state for this range. Now I'm taking this limit that delta e tends to 0. That means this gap will be closed. So indirectly I'm saying that the number of states at this delta e tends to 0 for energy state. Like there is no gap here. There is a discrete energy. So in each state, what is the number of then number of states there in this state E. So here is limit dE of delta E, whatever you want to see, tends to 0. Any questions still? Okay, then we move on. So we see how to calculate this density of state. So this density of state will depend on this factors P, and P is the dispersion factor, and number of dimensions. It will depend on number of dimension. So depending on P value, if we are considering bosons or some non-relativistic particles, we can take P equal to 1. Then we will get some relation um, between K and E in linear term, like some power will be there, but it won't be fraction. But for fermion case, this P is 2. So I'll get some relation like K is root over of energy, or some E is, I told you the opposite. So E is some root over of K, something like this. So this kind of relation I'll get for different cases, like for bosons, non-relativistic particles, I'll get like linear relation, and for fermions, I'll get some parabolic kind of relation between E and K. So um, I calculated this density of states. So it's like degeneracy in each energy state. So it's kind of degeneracy for each energy state. Now let's talk about distribution. Look, for Dirac, we have distribution um, of E as 1 over e to the power some energy of state minus potential, chemical potential, divided by kB T for fermion. This is here, there will be Q, and this Q value will be 1. So this is 1 over some e to the power epsilon plus, sorry, and writing the general form, this is epsilon minus mu over kBT plus 1 for Fermi-Dirac. For Fermi-Dirac distribution. For Bose-Einstein distribution, I'll have this as 1 over e to the power this factor minus 1. So this is for Bose-Einstein distribution. Now I have some system with some arbitrary number of energy states, and each state has some degeneracy gi plus 1 and so on, right? Then I want to calculate the number of I want to calculate the energy density of the system, U, small u, which is capital U divided by volume. So how I will calculate for a general system, and let's assume uh, okay, it's general, so don't assume. So we see there is a 1 by V factor here. That means per volume. Per volume factor, I can get it from this degeneracy. function which I have defined as um, number of states per volume for energy E. So 1 by V vector is taken by this GE. Now I want to calculate this U. What will be the U if I have a U? Um, U is the total internal energies. It's like summation of EI over some uh, number of microstates or WI, something like this. We calculate the total internal energy as this means number of microstates in each EI, then we'll sum them, right? So if I have a distribution for that, and this part will be taken care of by the distribution, then I have to write like this E part distribution, like let's say this FE. Then my in my distribution means um, this is a distribution for some particles like fermions or bosons. This is distribution for energy levels. So each energy level now has some density per volume or degeneracy per volume. Then I have to just simply multiply this factor GE here. So this formula will give me the total, not total, the internal energy per volume to, and it will go from 0 to infinity. Similarly, if I want to calculate the total number of particles per volume, I can calculate this as N over V. So this also I can write, and this I have to calculate the number of particles only, so I can remove this E. So this will be simply Fe Ge 0 to infinity. What this function does, it calculates the number of microstates or number of particles per unit volume. As we have seen from the last examples, like we used to calculate this number of microstates, then this distribution is similar to this calculation of microstates. And each microstate has some degeneracy, so we have to multiply with this distribution. Then we can calculate number of particles or uh, the energy per volume, the number of particles per volume or energy per volume, something like that. Or we can calculate the specific heat also by differentiating the formula. Specific heat formula is del U. Sorry, any questions?
Also, there's the equation dou u by dou t.
Yeah, do U over dot A, right? So this U I can write as I have defined small u previously. So small u is capital U over V. So I can get capital U from here. So this will be small u V. So I can write V. I am assuming volume is constant, so I can take V outside. Oh, okay. One second. Okay, yeah, okay, that's correct. Okay, I can take this V as to outside, as I am assuming volume is constant. Then I have to differentiate with this small u with respect to time. So small u I have already calculated. in general form, like this integration in terms of distribution and density function. So I can write my heat capacity. This is capital C. So heat capacity as V del over del T. So this is integration of E, F of E, C of E, limit from 0 to infinity. If I want to calculate specific heat capacity, then I have to divide by volume. Then this will be capital C over V. So only this sum. So specific heat also I can calculate from this formula. Right. So now come to problem part. Second question. So what is the question? We have given a system of non-interacting bosons, and they are obeying this dispersion relation, and they have spin 0, and we have to find the density of states per unit volume, then determine the critical temperature for Bose-Einstein condensation, then we have to find this fraction, and so on. So you see, it specifically mentions the spin of the particle. What is the importance of this spin? Um, let's say we have a spin half particle, then we can have plus half or minus half. So we'll have two different ways for this particle. So in that case, if we want to calculate the number of microstates, then uh, what's the Pauli exclusion principle says? For fermions, like they are spin-half, so fermions, no spin-half particle can no two spin-half particles can occupy a single energy states. So as they are degenerate now, they can sit. Uh, means they have different energy now, so I can put two spin half particles with spin 1 and spin half and minus half in a single energy state. So, like to say, for this spin, if we put this in magnetic field, this energy state will split. So you will see some substructure in each energy level. So we can put two spin half particles in single energy state. If you see, like in general, if but if you put magnetic field, you will see there is substructure. So each fermion is sitting in a single energy state. So it's like that. We calculate the microstates. Then there are two possible ways. Then we have to multiply with 2 with that microstates. Spin is half. So as spin is 0, there is only one kind of particle, only bosons. It has no other state. So let's proceed. We have dispersion relation. So we have to find the density of states now. So uh, I have not told you the formula. Space, space. So I have not mentioned this density of state. I can write as some integration over this space k over some um, normalization constant and some delta function a over h cross mu k. This is the dispersion relation. What this delta function does, it um, makes sure that this dispersion relation is obeyed. That means this function will be non-zero if e equal to h cross nu k, otherwise it will be 0 for all other uh, relations. So this delta function ensures that. Now, if we are in d dimension, then this will be d to the power dk, and this normalization constant will also be have some d factor here. Now, if you integrate, what will you get? Some volume in d space. Let's denote this volume as uh, omega d, and we will have this 2 pi to the power d, and we will um, dimension. We got a formula we derived in few slides back. Dn in terms of energy states, some constant C and Ck, and e to the power some n over p minus 1. So in that case, if we have this sorry, this is epsilon in the question. If you have this dispersion relation E equal to h cross mu k, that we have to obey. So this density matrix will depend on this epsilon as here n is dimension and p is this dispersion parameter. So we see our dispersion relation is linear, so p will be 1. So we will have what we will have e to the power d minus 1 as p is 0, and I am denoting n as d for this problem, e to the power d minus 1, and ck also we have. Okay, let me see the problem. Okay, okay. Um, we talked about this dispersion relation between this. Okay, we got some formula for volume like mm, n c n p c k to the power n over p, then e minus e0 to the power n over p, right? Then we did differentiation and we got dn. So you see, from this cn and ck will have the form like this is the proportionality constant. These all are proportionality constants. So if you substitute them, then you will get the coefficients h cross mu to the power d, as n is d here and p is 1. So you'll get this kind of density function for our problem. Okay, so what was the question? Find the density of state per unit volume G. So G is already per volume. So we have calculated GE as some volume in this case space over some normalization constant 2 pi to the power d, and we got epsilon to the power d minus 1 over proportionality constants which k d. So this is done. Now we have to determine the critical temperature for Bose-Einstein condensate in 3 dimensions. So D will be 3 now. So let's see. We have to calculate what? Uh, Critical temperature we have to find. So for that condition, T will be Tc, and for this case, the number of particles, um, Bose-Einstein condensate means at temperature Tc, most of the particle will be in a single ground state, and there won't be any exchange of particles between the surrounding and the system. So chemical potential will be zero. So, so the number of particles in this state is at temperature T equal to Tc and mu equal to 0. Right. Then we have to calculate n first. Then from n we will get some relation for Tc. Let's check. For Nc we have formula. Nc, no, nothing. So we have formula for number of states per volume. So what we got, this is as g of epsilon and distribution function, and this will be integrated as dg from 0 to infinity. So g of e we got already, and we saw that s is 0, that means they are bosons. So they are bosons means fd will be Bose-Einstein distribution. So this will be 1 over e to the power e minus mu. Mu is 0 now, so let's omit this. E over kp t minus 1. So this will follow this Bose-Einstein distribution now. And we are talking about the critical temperature at critical temperature. So we will put this T as Tc. Now let's rewrite this as 0 to infinity. We have g of e over e to the power e by kb t tc minus 1, and it will be integrated at the epsilon. So we have epsilon square here, and all other terms will be constant. You can pull out the constant outside, and if you, let's make it, then these constants are 2 pi um, so g of e, we got gamma d by e to the power d minus 1, and in the denominator we have 2 pi to the power d and h cross mu to the power d. So d is 3 now, so it's gamma of 3 epsilon square 2 power 2 pi to the power 2 and h cross omega, no sorry, it's d means 3 h cross mu 3. So this is our density function now. We'll put this in our formula. So we want this, and gamma of 3. Gamma of 3 means volume in 3 dimension. So previously I told you gamma of 1 in k space is mm, it was like how much? Gamma of 1, gamma of 1 was 2k, gamma of 2 was pi k square, gamma of 3 was 4 pi 4 pi k cube over 3, I think. Right. We I told you the coefficients. Then this density function was some coefficient to the power k to the power n, and this was cn. And this was the dimension in that term. So we'll get this kind of term. Then we'll pull out all the constants outside. Then if we do the integration over d epsilon, we'll get some zeta function. Like you can try doing this by hand, or you can put this in program like Mathematica. Then it will yield a zeta function like this. You'll get a formula like this: zeta of 3 pi square, and this will be kbtc over h cross mu. This is q. So this is for what? Number of particles per unit volume. So we got number of particles per unit volume as this. But what do we want? We want Tc. In the question, it is asked for the critical temperature. So from this relation, we can get Tc. Like we can take all other things up to the right hand side. So we'll have Kb Tc over h cross mu to the power 3 as n pi square over zeta 3. Then we'll have Kb Tc as h cross mu n pi square the zeta of 3 to the power 1 over 3. So this is the relation for critical temperature. Right. You got it so far, or you have some doubts?
No, sir, I have taken it down.
Okay. So this is the way, like for getting the number of particles, we have this formula. As we know from the spin, we are having bosons, and from that we can get the distribution for Bose-Einstein distribution like this, and we can derive this density function as from this formula. Then you do the integration, like getting a zeta function by doing manual integration is hard. You can put this in some program, then you will get this form for the number of particles, and from that you can calculate the critical temperature, right? Then we'll calculate the, what is the third question? We will come to the third question now. So this is done. We got a form for TC. Now it is asking us to find the condensate fraction. Condensate fraction means what? Okay. Okay. We have bosons distributed like this, and as we reduce the temperature, their motion will be slow down, and at some critical temperature Tc, they will behave like a single particle or single molecule, or whatever you can say. This state is known as Bose-Einstein condensate. So for that we need to reach a temperature as critical temperature. So in that state, if there are n number of particles, some n0 number of particles will be showing as this Bose-Einstein condensate behavior. So if we have n number of particles, and then out of those, n0 will be following Bose-Einstein condensate. So I can write my total number of particles as n equal to n0 plus uh, plus sorry, n0 is not the number of particles in Bose-Einstein condensate. This is the rest of the particles. The number of particles in condensate are that we calculated from here. At T equal to Tc, what is the number of particles we are getting? These many particles will be in Bose-Einstein condensate. Let's denote as and this as N1. So total number of particles will be some particles n0 which are not in condensate plus this number of particles which are in condensate. So total number of particles will be n0 plus n1. N1 is this much we calculated from this formula, which is zeta of 3 over pi square kb dc over h cross mu power 3. Now, what is the question? We are being asked what is the ratio n0 over n. Then from this formula we can get n0 over n. We can get n0 first. N0 is the number of particles which are not in condensate. So this is n minus this term. So now n0 over n will be, if I take n common, so it will be 1 minus this term divided by n. So zeta of 3 by n pi square kb dc or h cross mu 2 power 3. This is the condensate fraction, means out of how many fractions are being condensated. Like we have total n number of particles, and out of them n0 number of particles are not condensated. So then, okay, maybe it's unclear now. So if n0 is the number of particles which are not condensated, so this ratio it shows the number of particles which are not condensated, then we can uh, take as means total number of particles is n, right? So we'll have n over n as 1. So some fractions are now not condensated. So how many fractions are condensated? So I have to take difference from uh, like 1, like n0 by n. 1 minus n0 by n will give me the total number of condensated particles, or if it is condensated, then this is the answer. You got it right? Okay. Now, what is the next question? Hmm. Now, for this, and this is done. Okay. For this dispersion, is there any finite transition temperature in two dimension? If not, explain, or if there is, then find Tc. So Tc means T is the critical temperature, or transition temperature means at this temperature the bosons will transition from like many particles to a condensate state, means they will behave like a single molecule. Many particles will condensate and they will behave like a condensate state or single molecule state. So we need to find this Tc at this temperature they will condensate. So for two dimension we have to calculate now. We already calculated for three dimension here in B question. Now we have to calculate for three dimension. Sorry, two dimension. So uh, we won't do it from the beginning. So for three dimension case, we got the number of particles as 1 over 2 pi. Mm, so let me write the g function first. G of e was for three dimension or any d dimension was this omega d over 2 pi to the power d to the power epsilon t minus 1 h cross mu over d. So you see this integration was in and d to the power k. So I had to get rid of this k. So the delta function was delta of epsilon minus h cross mu k. So whatever the function was, I have to substitute for k. So for this k, I could have got epsilon over h nu. So from that, I can substitute and I will get this term. So this is the general form. Now we have calculated for three dimension. Now we will calculate for two dimension. So simply I have to put 2 here. So what will be the g? So it will be gamma of 2 but 2 to the 2 pi to the power 2 epsilon 1 over h cross mu square. So this is for this, then density function is for d equal to 2. So from that, then we can simply put this g in n formula. Like we have density function, then distribution function, then we have to integrate it from 0 to infinity. So I got a new kind of form for two dimension now. I'll put this, and I have distribution already. This is boson, so Bose-Einstein distribution. Then if I do the integration, I'll get some zeta function again. Now it's zeta of 2 over 2 pi, and this will be kb tc of square over h cos nu. So from this, I can get the relation for kb whole square. So from this, I'll get kb tc over h cos nu square as 2 pi n over zeta of 2. Then kb tc will be h cross nu over 2 pi n over zeta of 2 to the power half. This is for d equal to 2 dimension. So this is the critical temperature. Okay, this is the last slide. Okay. So this is the critical temperature in 2 dimension at which the condensation will occur. Right. So we calculated for 3 dimension. Now we calculated for 2 dimension. So from the spin, we can guess what is the kind of particle. Then we will take the distribution for the corresponding particle, and we'll calculate the density function using using that general formula and dispersion relation g of e equal to integration over d to power dk over 2 pi to power d, and there will be a direct delta function which will ensure our conservation of this dispersion relation. This will be a minus k. I am writing this for this question. Right. So now you see this particle is now spin half. So for this, the distribution function will be Fermi-Dirac. So this will be 1 over e to the power epsilon minus mu over kb t. Now it's plus, and distribution function we have like this, and from this distribution, sorry, not distribution, density function, we will get g of e, and you have already the distribution. Then if you want to calculate n or net capacity or whatever, you can simply put these terms and you calculate this. Right. Do you have any doubt? See, in this B question, you are asked to calculate the heat capacity. You know the formula I have told you a few minutes back. Then you can apply on that formula and you can calculate. So the steps are, you have to calculate density function, and from the spin you can guess the distribution, and you will put the those formula in the integration, and you calculate the number of particles or heat capacity like this. Right. Do you have any doubt?
No, sir. So as we done in the earlier case, we can do for the fermions also.
Yes, the distribution will be different now. It's spin-half particle, so Fermi Dirac distribution will be there. So similarly, we can do this also. So it's 5 now. So we'll stop here.
Okay,
Okay. So see you in next class.
okay, thank you, sir.
Bye bye.